So in this video, I'm going to be showing you how to find the derivative of a function. But before I do that, I have to make sure that we're ready for this, right? You need to recall, like from the last video, like from a minute ago, what the derivative is. And I want you to pause the video and write a sentence describing what the derivative is. Seriously. Alright, so here's my definition. I'm going to say that the derivative of a function is another function whose output value is the slope of the tangent to the original function at the given x value. I do not expect yours to be exactly the same. But I do hope that yours reference the fact that the derivative is a function. It is a function in its own right. And what that means is that function, this derivative, has output values. And those output values are the slope of the tangent line to the original function. Those are key components. I really would expect everybody to have, at the very least, function and slope of the tangent in your definitions. Those are the pieces you have to have, right? So we have this understanding that the derivative is a function, and it's a function that gives us back the slope of the tangent line. So the next thing we need to discuss then is how do we find this derivative? And I think the best way to lead you to an understanding of that is to ask you to recall, how do we find the slope of the line tangent to f of x at x equals 2, at some specific x value, like x equals 2? This was from yesterday's lessons. Pause the video. I want you to write down, what's the formula that we use to find the slope of a line tangent at x equals 2? That formula should be f prime of c equals the limit as h approaches 0 of f of 2 plus, remember that the formula we use had the c in it, but currently we want to say f prime of 2, right? And then we'll have 2 plus h minus f of 2 all over h. This is how we find f prime of 2. This is how we find the derivative at 2. We use this formula. That's how we find the slope of the tangent line at x equals 2. Now I have an amazing idea. What if we just didn't use a number when we found the slope of the tangent line? Like in that thing you guys just wrote down, you wrote down how to find the slope at 2. You plugged a 2 in there, right? So what if I just didn't use a 2? What if I just used an x, right? What I could do is I could say, hey, if I ever want to find the slope anywhere at any x value, let's just take the limit as h approaches 0 of f of x plus h minus f of x all over h, right? And I'd actually like to ask you guys to pause the video for a minute and make sure you still remember that this was always the slope of a secant line. Pause the video and think about that. Now that you're back, this x plus h represents, hey, we wanted the slope of the tangent line at x. So let's go to x plus a little bit more. Let's go a little bit to the right of x, and then let's be at x. We'll subtract those y coordinates. We'll divide by the x change, and then we'll take the limit as h approaches 0. We'll force this y value to get really close to that one, and we'll find the slope of the tangent line. What's amazing about this is this doesn't have any numbers in it. This has x in it. If we do this limit process over here, we will get the derivative function in all of its glory. And that means that if 1 minute somebody wants the slope of the tangent line at 5, we plug in 5. Then if somebody wants the slope of the tangent line at 3, we plug in 3. If they want one at -1, we just plug in -1. Once we've simplified this, we will have our derivative function, which will quickly give us any slope we want. Right? This is awesome. Furthermore, this is that thing that I said, hey, it's really important. It's going to mean something really, really awesome at some point in the future. Guess what? The future is now, which sounds really moving. Right? So let's get on to some examples. Let's do some stuff with this. So here we go. This example, I want us to consider the function v of x equals 3x squared. And I'm asking us to find v prime of x, which is the derivative of v of x. So based on what I said on the previous slide, the previous portion of the video, I think you guys should be able to set this up. So I'd like you to pause the video, set up how you would do this, and then sort of unpause to make sure you've got the same thing as I do, and then we'll work through it. Okay. So we just learned that if you want to find v prime of x, what we do is we simply say that v prime of x will be the limit as h approaches 0. And remember, the reason we have that limit is that we want to bring our two secant points right next to one another. So we do v of x plus h minus v of x all over h. Okay? Now I just need to evaluate this thing. I need to work through this thing the same way we did many times in Chapter 0 and in Chapter 1. Like, we have done this problem, right? As I've mentioned before, I know that a lot of you like to work out that v of x plus h part on the side, so I'm going to recommend we do that here. Right? We'll just step sideways, and we'll figure out what is v of x plus h. Well, this is my v function. It's going to be 3 times x plus h squared. That means it'll be 3 times x squared plus 2xh plus h squared. That means it'll be 3x squared plus 6xh plus 3h squared. A number of you, not a ton of you, but a number of you forget to put that 3 on the h squared there. Just be careful. I'm going to bring this back in and put it here. So I have my 3x squared plus 6xh plus 3h squared. And then I have minus v of x, so okay, that's just 3x squared. And on the bottom I have my h. So now we'll sort of bring this all back together. Surprise, surprise. 3x squared minus 3x squared, those things drop out. Surprise, surprise. There's an h in all of these terms, so I can divide it out. When I do that, I'm left with v prime of x equals the limit as h approaches 0 of 6x plus 3h. Now I just have to take the limit. Remember, the way we attempt to take limits is we attempt to evaluate this expression for the given value. So if I put 0 right there for h, this is just going to disappear, and I'm going to end up with v prime of x equals 6x. There it is. That's my derivative. Okay. Now I have one follow-up question, and here it is. Apparently I meant one pair of follow-up questions. My pair of follow-up questions are these. What is v of 5, and what does it mean? And what is v prime of 5, and what does it mean? So I want you to pause the video, go back, and answer those two questions. So first, what is v of 5? Well, very specifically, v of 5 will be 3 times 5 squared, which means it's 75. Okay? What does it mean? It means that v has a point at 5, 75. Okay? Now, what is v prime of 5, and what does it mean? Well, v prime of 5, according to the work that we just did, would be 6 times 5, which is 30. And what does it mean? It means that the slope of the line tangent to the original v function at x equals 5 is 30. Right? It's the same stuff we've seen numerous times before. The original function gives us a point. The derivative function gives us slopes of tangent lines. So we have one more example, and in this example I really want you guys to do this one largely on your own, although there's one little snag, and I'm going to explain it right here. So given the function h of x is 7x minus x squared, find h prime of x, then find the equation of the line tangent to h of x at x equals -3. When you guys set this problem up, when you find a derivative, you're going to have to do the limit as h approaches 0. But the bummer is, this problem already claimed h. Like, it's already using the letter h, so we really shouldn't use it again here. So we just need to use some other letter here, right? We can use any letter we want. H was just kind of what I was using before. You could use D for distance between the 2 points. You could use C because C is a nice letter. You could use M. I mean, why not? You pick some other letter. I'm going to use C in this instance just because I want to use C. Just please don't use H. You'll save yourself a lot of heartache on this problem. So pause the video, set this limit up, and work through it. So here we go. I'm going to need to take, not the limit yet, not ready for that yet. I'm going to write h prime of x is the limit as c approaches 0 of h of x plus c minus h of x all over c. And again, I want to point out, this was important because if we hadn't changed to c, we would have had like h's all over the place. Some of them would have been functions and some of them would have been numbers, and it just would have been a mess, right? So there's my setup, right? So next up, I've got h prime of x is the limit as c approaches 0. Now I need to do h of x plus c, so just like we've done before, we'll sort of slide sideways and do this. When I do h of x plus c, it's going to be 7 times x plus c minus x plus c squared. And I'm going to sort of skip a step here. 7x plus 7c minus x squared minus 2xc minus c squared. Right, so there we go, we've got that. We'll bring that back to our problem. So 7x plus 7c minus x squared minus 2xc minus c squared. So I've got all that stuff. Then it's supposed to be minus h of x, so minus 7x minus x squared. And then this thing is all over c. And I know this is a mess, but fortunately we've had practice with this before. We've simplified these things before. H prime of x is the limit as c approaches 0. And I'm going to, we'll sort of do this carefully. 7x plus 7c minus x squared minus 2xc minus c squared minus 7x plus x squared. That negative gets distributed through, right? And it's all over c. Again, horribly ugly. We've seen this before. We've cried about this before, right? But we know what's coming. We have negative x squared plus x squared. We have 7x minus 7x. And then all of the things that remain in the numerator all have a c in them, which means I can divide that c out, one of the c's out of all of them. That leaves me with h prime of x equals the limit as c approaches 0 of, let's see what's left, 7 minus 2x minus c. Okay. Last step to do this limit, we evaluate this when c equals 0. That means h prime of x is 7 minus 2x. This is my derivative statement. Now, I have the derivative statement. The last part of the problem asks me to find the equation of the line tangent at x equals negative 3. If you have not done that part yet, pause the video and do that on your own. In order to find the equation of that tangent line, I'm going to need a point and a slope, and you should know where to find those things. My slope comes from the derivative. My point comes from the original function. So I'll rewrite that down here so I can scroll the screen up or down depending on your perspective. And we wanted the line tangent at negative 3. Okay, so if I want the line tangent at negative 3, I will do h prime of negative 3. 7 minus 2 times negative 3, that's 7 plus 6, so that's 13. And what does that represent? This is my slope. Okay. In the other one, I'm going to do h of negative 3. That's going to give me 7 times negative 3 minus negative 3 squared, which is 9. This is going to give me negative 21 minus 9, which is negative 30. And so what did that get me? That gets me the point at negative 3 comma negative 30. I now have a slope and a point, and we know what to do. We're back to our old friend, well, for some of you, new friend, point-slope form. Point-slope form, we just do y minus y1, y plus 30, equals the slope of 13 times x minus our x-coordinate, so x minus negative 3. There is the equation of your tangent line. Okay. Now we know how to find derivatives. We know how to find this magical function which can find us the slope of any tangent line to a function. This is good stuff, and we're going to see where this is going to take us.